So, magnetic moment of nucleus, that is another parameter which we can study, which we can test, which for which the model can be tested. So, in this extreme single particle model, the magnetic moment, that also is given from that pairing thing. So, if it is even nucleus, even Z even N, then all the nucleons are paired, right. All the protons are paired, all the neutrons are paired, and for each pair the angular momenta couple to total angular momentum 0, and naturally its Z projection also 0. So, in any of the level, if we have 2 nucleons, 2 protons or 2 neutrons, the angular momentum of this plus angular momentum of this, that will add to 0, the angular momentum of this, angular momentum of this, that will add to 0. So, if this I call J1, this I call J2, then when these two combine to 0 0. So, total J is 0. So, this plus this, in general this plus this can be many other things can come. For example, if it is say 3 by 2, P 3 by 2, P 3 by 2, proton in the level P 3 by 2. So, 3 by 2 is the J value for first proton, 3 by 2 is the J value for second proton, then 3 by 2 plus 3 by 2, the total angular momentum quantum number can be, if it is 3 by 2, 3 by 2, that can be this plus this will be 3 and this minus this will be 0. So, all these values are possible in general, but then they are paired, that means they have chosen to have this angular momentum 0. Okay. So, their Z components are just opposite each other, that is also 0, and therefore, the angular magnetic moment coming from this pair is also 0, right. So, when the nucleons are paired, each pair contributes 0 magnetic moment, and if each pair contributes 0 magnetic moment, then and this is even Z even N, then the total magnetic moment of this nucleus is also 0. So, extreme single particle shell model will predict or will tell that for all even nuclei, the magnetic moment should be 0, and by and large this is consistent with the experimental observations. Okay. Next is odd A nucleus, a nucleus with odd A. So, here the prediction as well as the experimental results is that magnetic moment of the nucleus in ground state, right. We are talking of ground state. In excited states, the pairs can be broken and the particle one of the nucleon can go to some other level. So, pair can be broken. What we are talking is ground states, even nucleus in ground state, the magnetic moment will be 0. Now, next is odd A. Now, for odd A, all the nucleons except one is paired, right. Odd A, if the total number of nucleons is odd, either the Z will be odd or N will be odd. One of them will be even, other will be odd, then the total number capital A will be odd. So, if you have even number of protons, all these protons are paired up, there is no unpaired proton, even number. So, everything is paired up, and if it is an odd n, so an odd n means there is one neutron which is unpaired. And this extreme single particle model will tell you that all these paired neutrons, they will contribute 0 magnetic moment. Okay. So, this last neutron which is unpaired, only that will contribute to magnetic moment. So, we have to calculate the magnetic moment of this last nucleon, unpaired nucleon. Okay. So, when we were discussing deuteron, we talked about this magnetic moment. The magnetic moment what we measure is actually the z component, because when we set up the experiments to measure this magnetic moment, we somehow define a one axis, z axis. We apply magnetic field or we do something. So, that decides the z axis, and we actually measure only that z component of magnetic moment. So, first thing is that what we have to consider, what we have to calculate from the model and compare with the experiment is the z component of magnetic moment, mu z. And for mu z, the operator would be, remember, G L L Z plus G S S Z mu n over H cross, where this mu n is nuclear magneton. Mu n is nuclear magneton. It is unit for magnetic moment, and this is E H cross over 2 mass of proton. So, we always work with in these units. In atomic physics, when we talk of magnetic moment of the atom, that magnetic moment largely comes from the electrons. The Lz of electron, Sz of electron. So, and there we talk in terms of Bohr magneton, mu b, we write here mu b over H cross, Bohr magneton, and that Bohr magneton is defined again by similar formula, E H cross by 2 times mass of electrons. So, in an atom, magnetic moment comes from the electrons, also from the nucleus, but since nuclear magnetic moments is of the order of nuclear magneton, which is some 2000 times smaller than the Bohr magneton. So, normally when we talk of atomic magnetic moments, we just neglect this, but now we are talking of the magnetic moment of the nucleus alone. So, that will be in terms of this nuclear magneton, and the operator is here Lz. So, momentum is this magnetic moment is related to angular momentum, and angular momentum is coming from the orbital angular momentum as well as the spin angular momentum, and for that both the contributions are coming from here. And this GL and GS values, G values, they are different from proton and neutrons. So, for proton, you remember, for proton what is GL? For proton GL is 1 and GS is no, it is not 2. GS is 2 for electron, right. For electron GL is 1 and GS is 2. So, for point particles, point charged particles, that Dirac equation is okay, and electron is a point structureless particle, and it gives you GS equal to 2. For nucleons, proton or neutron, they are not structureless particles. Remember, a proton contains what kind of charge distribution inside it? You have 3 quarks, 2 by 3, 2 by 3, minus 1 by 3. Yes. Neutron also you have charge inside. The total charge on the neutron is 0, but as such it is not correct to say that there is no charge in the neutron. The total charge on the neutron is 0, but you still have that minus 1 by 3, minus 1 by 3 and 2 by 3. So, because of this structure, charge structure inside proton or inside neutron, that G value is very different, and very different for neutron, very different for proton. As such, if it is chargeless particle, you should not have a magnetic moment, but neutron does have a magnetic moment, because it is not strictly chargeless, you have a charge distribution, only the total charge is 0. Okay. So, for proton this GS is 5.5857. So, that is it. For neutron, how much is GL? How much is GL? 0. Yes, for neutron GS is 0, that classical orbital angular momentum, that is 0, and GS is minus 3.8260. Right, now you remember. Now, these values we can put here to calculate this magnetic moment Z component, but the problem comes with LZ and SZ, okay, because that last nucleon for which we are trying to calculate this, that last nucleon there also L and S has coupled to J. Okay. It is in whatever d5 by 2 or p3 by 2 or G or whatever. So, for that nucleon, actually for each nucleon we are looking for this last nucleon, but for each nucleon this L and S they combine to J, because that L dot S interaction is very strong. You substitute that L dot S term there in the Hamiltonian, only then you get those magic numbers, remember. So, that L dot S term is there, and once L dot S is there, it will combine L and S to J. That means, the Z component of L is no more definite, the Z component of S is no more definite, but Z component of J becomes definite, that is the LS coupling. Okay. So, you have JZ is equal to LZ and plus SZ, this is okay, right, this is this is fine, and the corresponding quantum number Mj is equal to Ml plus Ms, this is fine, and for a given state, a given energy state in this nucleus, you define that state by giving the value of J and Mj. So, L is there, S is there, J is there and Mj is there. S is anyway half. So, Sz can be either plus half or minus half depending on L. Ml can have any value from plus L to minus L in steps of 1, and important thing is this Ms or this Ml, that is not definite in that state, there can be mixture. In the same quantum state you can have more than one values of Ml and more than one values of Ms, but Mj has a fixed value, right. Mj is a definite value. Of course, energy does not depend on Mj unless you apply some magnetic field or do something or some internal magnetic field. So, all these Mj's will have the same energy level. So, in this energy level the quantum states are defined by this Mj. So, this Lz, it is not Ml times H cross, this Sz, it is not Ms times H cross, because Ml and Sz are no more definite. So, that is one issue. Second issue is, when we make measurement on a system, what we actually measure is some kind of average value, because we do not make measurement on one nucleus. We will make measurement large number of nuclei will be there, and all nuclei will not get aligned in one particular fashion. So, what you have to do, what you measure is an average value, and if you want to calculate and compare with the experiment, calculation also should go for that average value. So, what we need is mu z, expectation value of mu z or average value of mu z. In what state? In the state J and Mj equal to J, highest value of Mj, because we are trying to measure that z component of mu z by aligning all these things in that z direction, and therefore, the angular momentum or z component is also maximum of its value. So, m j is equal to j, j is anyway given for that state, and all varieties of m j's are possible with the same energy, they are all degenerate. We have to pick up this m j equal to j to calculate this expectation value, and then you have g l l z and plus g s s z. Mu n over h cross. This is the quantity we have to calculate. Now, 4 cases we have to discuss. First is j can be L plus half or j can be L minus half, right. Remember that P 3 by 2 and P 1 by 2. So, P is L equal to 1. So, 1 plus half is P 3 by 2 lower energy, and then 1 minus half P half is upper energy. Similarly, D L is equal to 2. So, you have D 3 by 2 and D 5 by 2, D 5 by 2 lower energy, D 3 by 2 upper energy. So, this 5 by 2 and 3 by 2 they are coming from L plus half and L minus half. For D state L is equal to 2. So, 2 plus half and 2 minus half, similarly for everything. So, J will be either L plus half or J will be L minus half. So, these are 2 cases, and then in each of these you have the last nucleon is proton or last nucleon is neutron, because for proton and neutron these G values are different. So, you have to consider them separately. So, first let me take this case which is easier to handle. J is equal to L plus half. Suppose we are taking this case, J is equal to L plus half. That means, we are talking of P 3 by 2 or D 5 by 2, right, or F 7 by 2, larger one, right. So, J is equal to L plus half. Now, if J equal to L plus half and we are asking m j equal to J, so that is the largest value. So, m j, but m j is equal to m l plus m s, and m j we are asking for J, that is L plus half. So, L plus half is equal to m l plus m s. Now, the values, possible values of m l are L 2 minus L in steps of 1. So, it can take values L, this can take values L, L minus 1, L minus 2, etcetera, and up to minus L, right. You may not have L minus 1, L minus 2, suppose it is P state we are talking of, L is equal to 1. So, 1 to minus 1, right. So, it will end here only if we are talking of S state, but the idea is it starts from L, it goes up to minus L in steps of 1 wherever it stops, and this m s can have only 2 values, half and minus half. Now, what combinations of m l and m s will give you m j equal to L plus half? There can be mixed states. I am ready to take more than one values of m l and more than one values of m s, but the condition is m l plus m s should become this much. So, from this list what value of m l I should choose and what values of corresponding m s I should choose to get this L plus half, the sum should be L plus half. What are the possible sets of m l and m s to give me L plus half? M l should be L and m s should be half, then I will get L plus half. Any other combination? No. So, fortunately for us calculations will be easy. M l is having only one value and ms is also having only one value, right, and that is ml should be equal to L and ms should be equal to half. Now, it is very simple now. If I say, if I know that ml is equal to L, then this Lz, expectation value of this Lz, what it will be? Because ml has only one value and therefore, Lz will have just that ml times h cross, that is L times h cross. There is no mixing. Similarly, Sz will be 1 by 2 h cross, and therefore, this mu z will be GL times LH cross plus GS times H cross by 2 and then mu n over H cross. So, GL L and plus GS by 2 mu n. If this last nucleon is proton, then this mu z is 1, GL is 1. So, it is L and how much is GS? 5.5857 by 2 n times mu n, which is L plus 2.7928 times mu n. And if I write in terms of J, which case we are dealing? This L is J minus half. So, this is J and minus half. So, 2.5928 times mu n. So, if the last nucleon happens to be a proton in this odd A nucleus, according to this extreme single particle shell model, the magnetic moment should be given by this expression, right. And if the last nucleon happens to be proton, then what happens? So, let me write it here. If this last nucleon happens to be a neutron and we are still discussing that same case, J is equal to L plus half. So, in that case you will have mu z equal to GL for neutron, how much? GL for neutron 0. So, this term does not come, as GS times GS divided by 2 times mu n, it is just GS 1, and how much is GS? 3.8260, right, and then divided by 2 times mu n, should be minus 1.9130 mu n. Okay, now discuss the case when J is L minus half, that means states like P half or D 3 by 2, right. So, those states where J is L minus half. So, let us discuss that case. J is L minus half. So, again look at this table. ML can take values L, L minus 1, L minus 2 and so on up to minus L, and MS can take values half and minus half, and this time what I need is that J should be equal to L minus half and Mj, which I am taking as J, should be L minus half, right. For calculating this expectation value, I am taking Mj equal to J, maximum value of J. So, if J is L minus half, Mj should also be L minus half. So, ML plus MS should be L minus half, and the values of ML are there L, L minus 1 and so on up to minus L, and ms can be plus half or minus half. Now, look at this table and tell me what are the possible sets of ml and ms which gives you ml plus ms equal to L minus half. These are the values of ml and these are the possible values of ms. So, what should I take for ml and what should I take for ms, so that ml plus ms is L minus half? L, right. Any other set possible? ml is equal to L minus 1, ms is equal to plus half, right. So, there are two possibilities, and since ml, ms are not definite, only mj is definite. So, both the states will be mixed up. So, when I write the state j and mj equal to j, it will contain this as well as this. Why I am talking in terms of ml and ms if they are not definite? I am talking in terms of ml and ms because I have to calculate this mu z, and that contains Lz and Sz, and Lz, the expectation value is ml times h cross, and this is ms times h cross. So, I need those ml and ms, that is why I am talking in terms of ml and ms. Now, this wave function that is here is therefore this wave function j mj equal to j, this wave function. It will be a combination of two wave functions, one in which, let me write this ml and ms. So, ml is equal to L and ms is equal to minus half and plus some other constant times ml is equal to L minus 1 and ms is equal to plus half. The j value, L value, those are definite, that I am not writing. ml is L, ms is minus half, is one component, this component, and also this component will be there with some fractions a and b. Right. Now, if I use this, you can write this as a psi 1 plus a b psi 2. If I use this wave function to evaluate this expectation value of mu z, let us see what happens. So, let me remove all this. So, now I have a psi 1 plus b psi 2 and then g l L z plus g s s z and this side a psi 1 plus b psi 2. So, this will be okay. Part by part I can take a psi 1 and this is mu z, let me write mu z first, mu z and that side a psi 1 plus b psi 2 here, mu z here and b psi 2 there, and plus cross terms a psi 1 here, mu z here and b psi 2 there, and plus b psi 2 here and mu z and a psi 1 here. All right, opened the bracket, 4 terms, opened the bracket. Now, this will be a star coming from here, a coming from here, it will be mod a square psi 1 mu z psi 2, and this is similarly mod b square, this is psi 1. So, psi 2 here, mu z here and psi 2 here, and these cross terms are going to become 0. Why? Why should they become 0? Because if you look at this psi 1, for example, psi 1 is ml equal to L and ms equal to half. So, in psi 1 ml has a definite value and ms has a definite value in psi 1, not in the actual wave function. Actual wave function is a psi 1 plus b psi 2, but in psi 1 ml and ms are. So, if you operate this mu z on psi 2 or mu z on psi 1, in psi 2 also ml and ms have definite values. So, when you operate this mu z on psi 2 and this is mu z, so you are getting back the same function with the corresponding eigenvalue out. So, when you operate mu z on psi 2, you will be getting psi 2. Separately you can look at Lz and you can look at Sz, that will be easier. You are getting back that psi 2 and psi 1 and psi 2 are orthogonal. So, this product is 0. Similarly, when you operate mu z on psi 1, you are getting back that psi 1. Separately you can look at this, you can look at this Lz operating on psi 1. Lz operating on psi 1, what it will give? ML is equal to L. So, Lz operating on this part will just give you L h cross times the same wave function. Similarly, Lz operating on this psi 2 will give you L minus 1 h cross times the same wave function. So, here after operation also it remains psi 2, some constants, and psi 1 and psi 2 will be orthogonal. So, these cross terms are 0 and hence you have just mod A square times this plus mod B square times this. So, two tasks, one to evaluate these expectation values in psi 1 and psi 2, and second task is to get the values of that A and B, in what proportion they have been mixed up. So, let us take the easier task first. Psi 1 mu z psi 1, let us calculate this. What is psi 1 mu z psi 1? What is psi 1? ML is equal to L and MS is equal to minus half, and mu z is equal to GL LZ GS SZ, and then this side ML is equal to L and MS is equal to minus half times mu n by h cross is also there, mu n by h cross, correct? Or okay, this is mu z. Let us first calculate only this much. Can we do that? This is equal to this is equal to this. Okay, mu n by h cross we will put at the end. So, there are two parts in this operator, one by one. First operate this Lz on this and then plus, and then we will operate this Lz. So, Lz part first, Lz part, what it will do? ML is equal to L, MS is equal to minus half, that is psi 1, and then GL is here, and Lz operating on this, what does it give? Lz operating on this, L h cross times this wave function. Okay, I have done only one part. This Lz I have operated on this and I have written here, and this thing is here, and next is Sz. So, I write ML equal to L, MS equal to minus half, and then GS and Sz operating on this, what it will give me? Minus h cross by 2. ML is equal to L and MS equal to minus half. Okay. Now, this wave function and this wave function are same. That is what I was telling. When you operate, you get the same wave function multiplied by the corresponding eigenvalue. So, that will be 1. So, it is just GL times LH cross, and from there it will be similarly minus GS times H minus H cross by 2. check minus signs. From here I am getting GL LH cross. So, GL LH cross, this wave function, this wave function, no more operator here, these are numbers. So, this is 1. Similarly, on this side here, this is GS coming here, okay, only one minus, fine. GS coming here, minus H cross by 2 coming here, minus H cross by 2 coming here. So, that is what is this quantity? This quantity we have evaluated psi 1 mu z psi 1, right. This is psi 1 mu z psi 1 is equal to GL LH cross minus GS H cross by 2. Just keep it here. So, this part I have evaluated, this part. Next is this part. Let us do mu 2 psi 2 mu z psi 2. Similar calculations. It is psi 2 mu z psi 2. So, here it is ML is L minus 1 and MS is half. I will not do that whole calculation this time. Psi 2 mu z psi 2, and psi 2 means ML is equal to and MS is equal to half, and then mu z is GL LZ GS SZ, and then the same wave function ML is L minus 1 and MS is half. And I want to do that those two steps here. This LZ, you have to substitute this LZ by L minus 1 H cross and this SZ by plus half H cross, that is it, rest will all normalized to 1. So, this will be GL times LZ, which is L minus 1 H cross, and plus GS times SZ, which is H cross by 2, right. So, the next thing is psi 2 mu z psi 2. This is GL times L minus 1 H cross and plus GS times H cross by 2. That is the second part. Now, the task is to get this A and B, slightly more involved, and for that I have to remind you some equations related to angular momentum. If you have any angular momentum, any kind of angular momentum given by the quantum number j, general talks. Okay. So, if you have any angular momentum given by j, you have these states j m j, where m j can take values from plus j to minus j in steps of 1. These type of states are there. Then you can define certain operators, j z anyway you know, right, j square and j z are there. Apart from that, you have an operator called j plus, you know this, j plus is j x plus I j y, and there is an operator called j minus, which is j x minus I j y. This is called, you know what is called, ladder operator, very good, wonderful, raising operator, and this one is lowering operator. And why it is called raising operator? Because j plus, if you operate on this j m j, what you get is a constant which is j minus mj, j plus mj plus 1, and then here j mj plus 1. Very good. So, the value of mj is raised by 1 unit, that is why it is called j minus, j plus. Similarly, if you operate j minus on this, you get a constant here, and then this j mj minus 1. So, that is why it is called lowering operators. I will be needing this j plus. So, this psi was a times psi 1, and what did we write psi 1 for? ml equal to L and ms equal to minus half, and plus b psi 2, ml is equal to L minus 1 and ms is equal to half. And this psi is j and mj is equal to j. This is the wave function which we expanded. Now, you apply this j plus, this with corresponding to this j here, apply this j plus on both sides. So, left hand side is j plus applied on j mj equal to j. How much is this? You can look at the equation and work out, or you can just remember this, mj has its highest value, mj equal to j, it cannot go up. So, raising operator operating on it cannot increase the value of mj by 1 unit, because it is already at its maximum value. Jz operating on this should give me 0. And that comes from here also, mj equal to j, when you put it is 0. So, if mj is already at its highest value and you try to raise it further, you get 0. Similarly, if mj is equal to minus j, already at the lowest value, and apply j minus on it, you will get 0, mj cannot go further down. So, this is 0. J plus applied on this must be 0. Therefore, j plus applied on the right hand side should be 0. So, j plus applied on this should be 0. J plus applied on this thing should be 0. So, let us calculate how much it is. Again we will do it in two parts, ml is equal to L, ms equal to minus half. Let us apply j plus to this portion first, then we will apply j plus to this portion, and we will demand that these two should add to 0, because this is 0. Okay. Now, j plus is L plus and plus S plus, because j is coming from L plus S, right. This j is L plus S. So, jx is Lx plus Sx, jy is Ly plus Sy, and therefore, L plus and L minus and S plus everything will combine similarly. So, j plus will be L plus plus S plus. This should be applied on A times, A we will put later, A we will put later, apply on this, j plus applied on this. So, L plus plus S plus applied on ml equal to L and ms is equal to minus half. Again two parts, L plus applied on this is equal to L plus applied on ml is equal to L and ms is equal to minus half, and plus S plus applied on ml is equal to L and ms equal to minus half. Okay. L plus will do nothing to spin part, but L plus will apply on this. L plus applied on ML equal to L, what should it give? ML is equal to L. ML can take values from plus L to minus L in steps of 1, and this is ML equal to L already at its highest value, and then you are trying to raise L plus operating on this should give you 0, right. So, this part is 0. S plus operating on MS equal to minus half, this is spin operator will operate on this spin part. So, this part will be unaffected, and MS is equal to minus half. Yes, it can raise, MS can go to plus half, and therefore, you should use it now. So, you have S is equal to half, look at the spin part now, spin part S is equal to half and MS is equal to minus half, and you are trying to operate S plus. So, if you look at here, this is half, this J is this S. So, this is half and MJ is MS, that is minus half. So, half minus minus half. So, this is 1. J is half, MJ is minus half. So, these two cancel and 1. So, this whole thing is just 1. This whole thing is just 1, and it is just this MJ going to MJ plus 1. So, this part is now ML is equal to L, that this is space part not affected by spin operator. So, ML is equal to L and MS is equal to plus half. Okay. So, I have operated J plus on this one, the first term here. I have to yet operate J plus on this one. So, keep this in mind, J plus on the first. So, let me do it here. This I can now write J plus operating on ML equal to L, MS equal to minus half. This I have done, and what I get is ML equal to L and MS equal to plus half, right. Next, J plus operating on ML equal to L minus 1, MS equal to half, operate on this. So, once again this is L plus operating on ML equal to L minus 1 and MS equal to half, plus S plus operating on ML equal to L minus 1 and MS equal to half, because J plus is L plus S plus, equal to here L plus will operate on this ML, this part, space part, not spin part. Spin part will remain unaffected, and here ML is L minus 1. So, it can raise. So, go here, in place of J you will have L, and in place of MJ you will have L minus 1. So, L minus bracket L minus 1. So, this will be 1. Here J is L, MJ is L minus 1. No, you are doing this. Yes, so, MJ is L minus 1. So, you put L minus 1 here, and J is L. So, L plus L minus 1 and plus 1, 2L. So, it is square root 2L, this part I am writing, this part, square root 2L. Now, what is ML? L, and MS is equal to half. So, this is this part, and the other part S plus here, MS equal to half here, what will it give? 0. ms is already at its highest value and then you are trying to raise it s plus. So, this is going to give you 0. So, that is it. So, this is that second part. Okay. Now, you demand that j plus operating on this whole thing should be 0. So, 0 should be equal to a times what? This one, plus b times what? Square root 2l and these two wave functions, look at these two wave functions, they are same and this should be 0, that means a plus b square root 2l should be 0, right. ml equal to l, ms equal to half here also, there also. So, you can take that wave function on one side and you will have a plus b times square root of 2l. So, you get this equation a plus b times 2l is equal to 0 or a is equal to minus b square root of 2l. Another equation of a in a and b is very simple, your a square mod a square plus mod b square should be equal to 1, because the wave function you had written as a psi 1 plus b psi 2. So, if psi 1 is normalized, psi 2 is normalized, psi is normalized, then mod a square plus mod b square should be equal to 0. So, you have these two equations, right. So, mod a square is mod b square times 2l from here and plus mod b square, and that should be equal to 1, and therefore, mod b square should be equal to what? 1 by 2l plus 1, and your mod, okay, I will only need mod b square, and mod a square, can write it from here, it is b square times 2l, mod b square times 2l. So, it is 2l by 2l plus 1. I have everything with me. I have this part, I have this part, I have a square, I have b square, and I can put all these things together to write the expectation value of mu z. Which one? Here?
Yes, sir. ml is equal to L minus 1, ml is equal to L also.
See, this L plus is operating on this, okay? And L plus when operates on this, ml is raised by 1 unit. So, this becomes L, this ml becomes L. So, when you operate this, this becomes ml equal to L. And this part is anyway 0, this do not get this one is 0, S plus operating on this is 0, and L plus operating on this has raised ml to ml equal to 1. That is why these two terms are same and can be taken common.